Recording in progress.
Hello, everyone, and welcome back. We are in the MHF4U course. This is the grade 12 University Advanced Functions. We are on Unit 1, Lesson 4, and this is just one of one. So we only have one lesson today, and the topic is fairly straightforward. Essentially, all we're doing is writing equations for applications. In specific, the concepts we'll be looking at will be, again, we need to apply the change of base formula. We'll be evaluating expressions and solving for exponents, modeling exponential relations, writing equations for exponentials with different bases and solving for exponents. And if necessary, we'll graph an exponential relation. I think we have one we have to do, so I left that till the end. And in general, we'll know things have gone well because you will be able to model exponential relations and solve for some unknown exponents. And so I bring the change of base formula as something we should remember, where if you have log base b of a, that's equal to log of a over top of log of b. Additionally, I wanted to review some calculations and some equations we're going to be solving for. So in example one, it's called calculations, and we're going to evaluate the following. And I have the Desmos scientific calculator and the Desmos graphing calculator today. So let's go ahead and solve. Letter A, we have 2 times log base 3 of 6. Using the change of base formula, we can make this equal to 2 times log base 6 divided by log of 3. Okay, so remember, the 2 will get multiplied into the numerator. And so typing this into the calculator, we have log of 2 log of 6 divided by log of 3, and we end up getting 3.2619-ish as a solution. So pretty straightforward. For letter B, what do we do here? We have 10 times the log base 4 of 10 divided by 7. I would note that you can rewrite this as 10 divided by 7 multiplied by log base 4 of 10. And then using the change of base formula, you can make this 10 times log of 10 divided by log of 4. And this will then simplify down to 10 log of 10 divided by 7 log of 4. And let's fix up this 4 here. That one was questionable. Okay, using the Desmos scientific calculator, we can type this as log. So we've got 10 log of 10 divided by 7 log of 4. And so as a solution here, we get 2.3728. So we can go ahead and box those, and those will be our solutions. Okay, so typing these in, again, we're going to make the assumption that you'll be using the change of base formula, because if you have the log base whatever button, you can just type these in directly and be able to get to the right solution. Okay, let us continue. The other kind of common equations we'll be solving will look like this. Letter A is a question you would have solved in previous math courses where you would have been given some sort of exponential relation and be expected to type it in. Namely, x is equal to 40 multiplied by 2 to the power of 30 divided by 5. Our calculator can handle this. We can just type this in as we see it. So this will be 40 multiplied by 2 to the power of an exponent, 30 over 5. So here, x will be equal to 2,560. If you so wish, you could simplify out the exponent. So you might notice that 30 divided by 5 is 6. And so you could write this as 40 multiplied by 2 to the power of 6, but you end up getting the right solution. So I leave the details for exactly how to solve that to you. Letter B is the most common type of log exponential relation we're going to be solving, and that is 40 is equal to 100 multiplied by 0.5, 1/2 to the power of x. My recommendation, we make 1/2 just equal to 0.5. It's less cumbersome that way. So 40 is equal to 100 multiplied by 0.5 to the power of x. Next thing we want to do is to divide both sides by 100. So then we're going to end up with 40 over 100 is equal to 0.5x. Next, we're going to write this in logarithmic form. So it'll be log base 0.5 of 40 over 100 is equal to our x value. And applying the change of base formula, we end up getting x is equal to log of 40 divided by 100 over top of log of 0.5. It's worth noting that if you needed to, you could go ahead and simplify 40 over 100 as being equal to 0.4. And if there are such simplifications available, that is a recommended way to proceed. But I wanted to show you that if you wanted to leave it as a fraction, you could do that. It's just a little bit more cumbersome to work with. But again, we're not too worried about that. So we type this into our calculator. So log of 40 over 100 divided by log of 0.5, we end up getting as a solution here, x is equal to 1.3219-ish, of course. And we'll go ahead and circle our answer. Now, if we want to check to make sure this is done correctly, we can take our answer and substitute it into the original. So if we take 100 multiplied by 0.5 and raise it to the power of 1.3219, we get approximately 40. I did mention on earlier lessons that when you use exponents, it's quite sensitive with respect to the number of decimal places you use. And so rounding prematurely can cause your answer to be seemingly off by a lot more than maybe you're comfortable with. So a few extra decimal places wouldn't go amiss. Lastly, letter C, we have 4,000 is equal to 1,000 multiplied by 1.08 to the power of x over 5. Again, because of bed mass, because that's what we need to do. So if you would like, we call this bed or ped mass. We can't multiply 1,000 times 1.08 because the 1.08 is trapped by the x to the power of 1/5. So that needs to be resolved first. So it's a common mistake I see here where people just take 1,000 times 1.08. We cannot do that because of bed mass. So first thing we want to do is divide both sides by 1,000. So 4,000 divided by 1,000 is going to be 4 is equal to 1.08 to the power of x on 5. Using the change of base formula, we end up with log base 1.08 of 4 is equal to x over 5. Multiplying both sides by 5 yields that 5 times the log base 1.08 of 4 is our x value. And you might notice this already looks quite familiar to the first question we already solved, just with not as pleasant looking numbers. So using the change of base formula, we can finally write this as x is equal to 5 times the log of 4 divided by log of 1.08. And so typing that in, log, so 5 log of 4 divided by log of 1.08, we get x is equal to 90.0647 after rounding. And so if you were so interested, we could sub this into our equation to verify that this is correct. So in terms of a check, we want to confirm that 1,000 times 1.08 to the power of 90.0647 0.0647 over top of 5 is about 4,000. So let's have a look. 1,000 multiplied by 1.08, the power of 90.0647 divided by 5. And you can see we get about 4,000. So we'll put equals 4,000 because it's close enough for our purposes. Okay, so exponentials also have the added benefit of that it is extremely easy to verify our solutions are correct or not. Okay, so these are the calculations you can expect to run into, either just evaluating it directly, evaluating for an exponent, or evaluating for something in an rational exponent. These are the most common things you can run into. I do have an example where we solve for something else, but again, I will provide that in the examples below. And so in general, when you're going to solve these things, when I go through them, they're going to look pretty reasonable, but I do encourage you to try out the support questions, verify that those are done correctly against the answers in the back of the book, and then try out the key questions. So the book lists some problem-solving strategies you can use, and these are and using problem solving using logarithms uses the same strategies that would be solved in any mathematical problem. In general, read the question at least once to completely understand what is being asked. If you have any questions about something in there, make sure to I try to identify those. Identify factors that will be used to recognize and solve the problem. Oftentimes, this takes the role of something called a given. So what is the given information? Select appropriate tools to solve the problem. Common answer doesn't show up as much in logarithms, but make sure you answer the question that is being asked. Sometimes we solve a question and we think we're done, but we actually need to do an extra step. That doesn't occur as often, but it can. And now afterwards, we have to check the reasonableness of our answer. So does our answer kind of make rough sense? So this is where having some knowledge about powers to basis to given powers can say that it looks approximately. So for example here, if in letter C with 4,000 is equal to 1,000 times 1.08 to the power of x over 5, 90 might seem like a correct answer. Maybe that seems plausible, I suppose. But if I'm not sure, I can always just check to make sure the answer is correct. Okay. So here's the main formula that we're going to use. So we have exponential models can be used to model exponential growth or exponential decay. So we have some sort of population, either say an element or like a biological population that grows or decays in proportion to itself. Okay. And so the general formula is P of t is equal to P naught times B to the power of t over D. So P sub 0 or P0. Most often we pronounce this as P naught. I pronounce it P sub 0 just so that way it's very clear that we're talking about a subscript. What do we have here? P is the population that we care about. So what does it grow to or decay to? P naught is the initial population. T is time. D is the period. When it comes to writing exponential equations, students have the most problem with the period by far. But again, we have plenty of examples for us to cover every case that will come up. B is the growth. So if B is greater than 1, that's a growth. If B is between 0 and 1, then it's decay. Don't worry about negative bases here because that doesn't make any sense. There are other variations of this formula. So sometimes people might write this as M is equal to M naught times B to the power of T over D. And they use M to mean or you can also write this as, say, f of x is equal to f0 times b to the power of t over d. Just know that these all mean the same thing. insofar as they're describing some sort of exponential growth. And I should say that it's b to the power of x over d. I'm just used to t because for exponentials, typically t is time is always used. Sorry, excuse me. Okay. So for the first 4 questions, so it's example 2, parts A, B, C, and D, we're just going to practice writing equations. So this is practice writing equations. We're not going to do anything with them because we have plenty of those to choose from. I think we go up to like 10 examples of these. So we're going to just practice with writing out equations. And so our general equation is capital P is equal to P naught times B to the power of T over D. I'm going to write this a little bit lower so we have more space. Capital P is equal to P naught times B to the power of T over D. And again, if we were talking about elements, we could easily use M for mass, but again, P is a pretty standard. And so before even reading the question, something you might want to consider is writing down your given information. So we might want to know, what is P? What is P naught? What is B? What is T? And what is D? Okay. Now, since these are equations, we're not going to be solving for anything, but you'll see the benefit of this method soon enough. Okay, so we have an initial population of 400 bees. So initial means starting, and if it's a starting amount, that's going to be P sub 0. So P sub 0 will be 400. Of bees, right, they double every 3 days. Okay, so the base amount of bees doubles. So if we're doubling, that's going to be our base. Now, our time t is going to be in t days, and our p is going to be just a population of bees. And d is the period. How long does it take for the bee population to double? Well, it takes three days to do that. And so capital P will be equal to, the initial population is 400, multiplied by B, which is going to be 2 to the power of T over 3. And this is the general equation that would describe this. And if you so choose, and in fact, I will go ahead and do this, we have our P of T. I just use capital P here because the book uses capital P and sometimes it uses P of T, but they mean the same thing. But essentially, this is what the equation look like. So after 3 days, you would expect the number of bees to double. So if T happened to be 3, then we would have, say, 800 bees. And after 6 days, you'd expect it to double. So it would go to 8 and then 1600 bees and so forth. Okay, so these are what the equations can look like. Letter B, the population of a certain animal species decreases at a rate of 3.5% per year. You have counted 80 of the animals in the habitat you are studying. Okay, so again, we have P is equal to P naught times B to the power of T over D. So this appears to be a population. Capital B is just a population. P naught, little b, little t, and d. Okay, P naught's the easy one. So that's the initial amount. And the initial amount is 80 of them. B is the base rate to K. So for percents, so if you have a base that's equal to a percent increase or decrease, we write it as 1 plus or minus the percent as a decimal. That's how we handle a percent increase or decrease. So we're decreasing at 3.5%. So our B value is going to be 1 minus, and I'm going to write this in red, 1 minus 3.5%, which is equal to 1 minus 0.035. And on our calculator, if you take 1 minus 0.035, we get 0.965. So what this means is if your population of a certain species decreases by 3.5%, that means you are keeping 96.5% of the population. So we maintain 96.5% of the population. T is the time. We're talking about this per year. So we'll put this in years. And we notice here the period, how long does it take for the animal population to decrease by 3.5%? Well, it happens per year. Per year equals 1. And so our equation for this will be capital P is equal to 80 multiplied by B, which is going to be 0.965 to the power of T over 1. But T over 1 looks like a little bit strange. So instead, we could write this as 80 times 0.965 to the power of just T. And if you notice, this kind of equation was one of the ones we started with at the start. In letter B here, where we had 40 is equal to 100 times 1/2 to the power of x. And so typically, when you see things like per year or each year, that means your D value is going to be 1. Okay. This could also be like, say, per day, could also apply in this situation. But if it's per single unit, that means D is going to be equal to 1. Okay. Suppose there's 200 of a certain species, and this species decreases by 7% every 5 months. Okay, sounds good. Let's have a look. So capital P will be equal to P naught times B to the power of T over D. So P appears to be your species. P sub 0 is the initial amount, so that's going to be 200. We have our base, our T, and our D. So in this case, if you notice, we decrease by 7%. So that since it's a percent, we're going to go 1 minus 7%, which is equal to 1 minus 0.07, which will be 0.93. I wonder if the calculator can do this. 1 minus 7%. No, I can't quite do that. It's okay. But if you take 1 minus 0.07, you see you get 0.93. The time, we can see it's in months. So we'll go ahead and write that. And how long does it take for the population to decrease by 7%? Well, it takes 5 months for it to do that. And so our equation then will become capital P is equal to 200 times 0.93 to the power of T over top of 5. So you can expect after 5 months, 7% of the population goes away or disappears or what have you. And then another 5 months later, another 7% of the original amount would go away. Okay. This is the kind of last, we didn't do an increase one, but that's okay. The first question we have in the examples what we're going to solve is going to have an increase one, so we're not worried about that. Letter D, we have radon, has a half-life of 25 days, and there is an initial amount of 300 grams. So since we're talking about amounts, typically this is where you want to use M for mass, but again, we're not too caught up on that. So since we're talking about grams, we'll use capital M is equal to capital M sub 0 times B to the power of T over D. Again, the M versus P is not a big deal either way. So M is going to be the mass of radon. M sub 0, how much do we start with initially? Well, it's 300. B. Now, what's the base growth? So this is where it's a little bit of unusual. When you see half-life, that literally means half. So this is saying that the way we describe half-life is, or the way its half-life is described to us, is that there's a certain amount of time until half of it goes away. So in the case of radon, it's in T is time in days. And D is going to be 25 days. And so what this means is that it takes 25 days for half of the radon amount to go away. So if you have 300 grams, you could expect that 25 days later, you will have 150. And then another 25 days later, you'll have half of 150, which will be 75. And so the equation for this ends up being capital M is equal to 300 times 1/2. And if you want, you can make the substitution that 1/2 equals 0.5. That's fine. To the power of T over 25. And so if I was going to graph this on the Desmos graphing calculator, what would this look like? Or am I going to crash my computer? Nope, we're good. Okay. So here, if I write in 300 multiplied by 1/2 to the power of, we'll go x over 25. We end up getting this shape. So you can see on month 0, we have 300. And then 25 days later, we have half of it has gone away. So that means we've gone from 300 to 25. And if we go another 25 days later, you can see we're now at 75. So we've gone from 150, 75. Then you would expect what's half of 75? That's about 30. That'll be 37.5, and that'll happen at day 75. So you can see every 25 days, half of it goes away. Okay, and again, you can try this on Desmos. Luckily that we did record this so you can see what it looks like as well. Okay, let's continue. So now we're going to be solving exponential relations. So we're going to write an equation that models each relation and solve for the missing component. So for letter A, the bear population increases at a rate of 1.2% per year. If there are 400 bears in a local park, how long will it take for the bear population to reach 500? Okay, so our equation is going to be P is equal to P naught times B to the power of T over D. So P sub 0, B, T, and D. Okay, so what's our population? Well, we want to get to 500. P naught is how much we started with initially, so that's going to be 400. Our B value is the percent, is going to be the increase. This time it's 1.2%, so it'll be 1 plus 1.2%. So this will equal 1.012. T is the time. We don't know what that is. We don't know how long it will take for the pair population to go from 4 to 500. And D is the time. And so you can see we've got that per year, so D is going to be 1. So our equation we're going to be solving will be 500 is equal to 400 multiplied by 1.012 to the power of t over 1, but instead of t over 1, we can just make it t. And now we'd like to solve for t. Easy enough. We divide both sides by 400. So if you were to take 500 divided by 400, you get 1.25. So 1.25 will equal 1.012 to the power of t. And so using the exponential equivalent, t will be equal to log base 1.012 of 1.25, which will be log of 1.25 divided by log of 1.012. And so if you type that into your calculator, so this will be log of 1.25 divided by log of 1.012. We get that this bear population will take about 18.7, and these are in years. And that's what all of these questions are going to be looking like. Identify the parts we're given, use the equation, and go from there. If you want to check to make sure we did this correctly, we could just verify it in this line. And so if we take 400 multiplied by 1.012 to the power of 18.7, oh, not 187, 18.7, we get 499.96, which is about years. Okay, letter B. A local black 5 population contains 700 members. If they double in number every day, how long until they reach 10,000? Sounds like these ones were in Pickle Lake, so let's have a look. I did work in Pickle Lake, which is why I know that this can occur. Okay, so we have P is equal to P naught times B to the power of T over D. So we have P naught, our base B, T, and D. So let's see what we've got for each of these. So P is what we want to end up with. And so we want to end up with 10,000 of these things. P naught is the initial amount. So that's going to be 700. B is the base growth. And we can see that they are doubling every day. So if you're doubling, your base is going to be 2. T is the time. We don't know what it is, but we know it's in days. So we can put a question mark, but it will be some amount of days where this occurs. And D is the period. So we can see that it's every day, which means that's just going to be 1. And so our equation will be P, oh, not P, it'll be 10,000, because instead of P, we'll put 10,000. P naught will be 700. B will be 2. T will be the thing we're looking for, and D will be 1. And so we got a little bit more space. So we can rewrite this as 10,000 is equal to 700 times 2 to the power of T. And from here, we go ahead and solve. So we want to take our 10,000 and divide it by 700. So we don't get quite a nice number, but it does reduce down to 100 over 7. So we can say 100 over 7 is equal to 2 to the power of T. Rewriting this in exponential equivalent, we have this as log, oh, perhaps I want to write T. T is equal to log base 2 of 100 divided by 7, which will be equal to, I put 2 G's in log, let's not do that, which will be log of 100 divided by 7 over top of log of 2. And so let's see what we get. So type in our logs. This is why we practiced the fraction portion from earlier, was just to confirm that, this works. And again, if you didn't know that 10,000 over 700 reduces down to 100 over 7, you could write it as 10,000 over 700. That does not change the calculation. If you were to round it with some decimals, just make sure to include some extra decimals, lest you run into your answer may differ slightly from mine. And we end up getting the solution to be 3.83 or so. I guess we should round it to 3.84 days. You might be thinking, that sounds like it happens pretty quick. Well, if you think about it, if we start with 700, at the end of day one, there's 400. At the end of day two, there's 2,800. At the end of day three, there's 5,600. And at the end of day four, we're over 10,000, which is why it's about 3.84, because it's not quite 4, but it's just pretty close to it. Okay. Let us continue. Letter C, chocolatium has a half-life of 1 minute. And if there's a 1,000-gram sample, how long is there until 200 grams is remaining? Okay, so they're talking about grams here. So we can use M is equal to M naught times B to the power of T over D. So M naught, B, T, and D. The mass we're going to end up with will be 1,000. M naught is the initial amount, so that'll be 200. B, what's it doing here? Well, this is half-life, so that's going to be 1/2, so we'll call it 0.5. T is the time. We don't know how long it takes, but we know it's in minutes. And D is the half-life. How long does it take for this to occur? It's got a half-life of 1 minute, so it'll just be 1. So it'll be similar to the ones above. So we can write this as 1. Oh, I have this backwards. Should be a 200 gram amount, and we started with 1,000. Because remember, the chocolatium is a chocolate bar that's disappearing over time. If you've ever left it at a place of work, half of it tends to leave the table every time you look at it. We have 200 is equal to 1,000 times 0.5 to the power of just t, because remember, in this case, it was t over 1, which becomes t. Divided by 1,000, we get 0.2 is equal to 0.5t. In logarithmic form, we end up with t is equal to log of base 0.5 of 0.2, which will be log of 0.2 divided by the log of 0.5. And so we could type that in. So this will be a log of 0.2 over log of 0.5. And so we get t is equal to about 2.32, and this is minutes. This answer seems to make sense, since if you take half of 1,000 is 500, half of 500 is 250, so that's about 2 minutes, which looks good to me. Letter D, we have uranium-235, has a half-life of 4.5 billion years. Determine how long a 3-pound sample will take to decay to 2 pounds. Okay, so we're talking about a mass again, this time in pounds. So we'll write this as capital M is equal to M naught times B to the power of T over D. And so we'll write down our givens. So what's the final mass we're interested in? Well, that'll be 2 pounds. How much do we start with? 3. What's the base growth and decay? Oh, and this is a case where the 235 happens to be just the name of the element. So that in this case, we actually call it the isotope of the element. So this is the stuff that's used to make nuclear power. Okay, so B is the base, and we're talking about a half-life. So that's going to be 1/2, which we'll call just 0.5. T is the time. We don't know, but it's in billions of years. And D is the time. How long does it take for half of it to go away? Well, it takes 4.5 billion years for half of it to go away. Okay, so let's go ahead and type these in. So we're going to be solving for a mass here of 2 is equal to the initial mass, which is 3, times 0.5 to the power of t over 4.5. So we've already solved this kind of equation. Divide both sides by 3. So we end up with 2/3 is equal to 0.5 to the power of t over 4.5. Using the logarithmic equivalent, we end up with t over 4.5 is equal to log base 0.5 of 2/3. And this will then be equal to log of 2/3 divided by log of 0.5. But then if you notice here, we need to multiply by 4.5. And so t will be equal to 4.5 times the log of 2/3 divided by the log of 0.5. So let's type this in. So 4.5 times the log of 2/3 divided by the log of 0.5. And so we can see that this will take 2.63-ish billion years. And does this answer make sense? Well, it takes 4.5 billion years for half of it to go away. So you would start at 3. So after 4.5 billion years, you'd have 1. You would have 1.5. So 2.63 sounds plausible. If you don't believe that's the case, you can always check your answer in this version. So we could check t equals 2.63 to see if we get approximately the right answer. So if we take 3 times 0.5 to the power of 2.63 over top of 4.5, yeah, we get about 2. And again, we're talking billions of years, so give or take a few 10 million years. Not a big deal when you're in the land of billions. Let's continue on. Letter E, suppose a fleet population triples every 20 hours. If a local population contains 1,500 members, how many fleas are there after 120 hours? Okay, so the equation we're going to write is capital P, because of the population, is equal to P naught times B power of T. And so writing down our givens, P equals P naught, B, T, and D. And so how much do we end up with for our flea population? We actually don't know. So we're solving for something different today. How many fleas do we start with? Well, 1,500. Uh, how fast are they growing? Well, they're tripling, so the base will be 3. T is the time of it. So how long are the fleas doubling for or tripling for? This is going to be 120, and this will be in hours. And how long does it take for their population to double? To triple, it takes 20 hours. And so capital P will be equal to 1,500 times 3 to the power of 120 over 20. So P naught was 1,500, B was 3, T was 120, and D was just normal 20. So this is the kind of question you expect might have run into in a previous course. These are mixed in with some of the ones you'll be solving in the booklet just because they don't want you to solve the same thing over and over again ad nauseum. And so we take 1,500 multiplied by 3 to the power of 120 divided by 20. And we can see we have a population of fleas of 1,093,500 fleas. So lots and lots of fleas. Okay. Curium 240 has a half-life of 27 days. Determine how long a 900-gram sample will decay to 400. Okay. So here, m is equal to m naught times b to the power of t over d. And so we have m naught, b, t, and d. And so keep in mind, this is the name of the element, so we don't need that. But it has a half-life of 27 days. We have a 900-gram sample to decay to 400. So we're going to solve for t. That'll be our question mark. So how much are we going to end up with? Well, that'll be 400. Our initial amount is 900. Our base is half-life, so that'll be 0.5. And how long does it take for half of the curium to go away or change into something else? It takes 27 days. And so we don't know what t is, but we know t will be solved for in days. And so we end up with 400 is equal to 900 times 0.5 to the power of t over 27. Dividing both sides by 900, we end up with 4/9 is equal to 0.5 to the power of t over 27. Taking the logarithmic equivalent, we have t over 27 is equal to log of 0.5 times 4/9, which will be equal to log of 4/9 divided by log of 0.5. Multiplying both sides by 27 yields t being equal to 27 multiplied by log of 4/9 divided by log of 0.5. Okay. Well, let's have a look here. So we have 27 times the log. So 27 times the log of 4 divided by 9 divided by log of 0.5. And so this will take about 31.58 days. And again, this makes sense. If after 27 days, half of it disappears or transforms, 900 goes to 450, which is okay. Oh, I don't know if the rest of the lesson of next time. Letter G, the world population in the year 2000 was approximately 6.08 billion. The annual rate of increase is about 1.26%. Suppose the rate of increase continues to be 1.26%. Write an equation to model the population. Okay, so here we know that the population will be equal to 6.08 billion. Now, what's the B? So B, since it's an increase, will be 1 plus 1.26%. So B will be equal to 1.0126. And this is going to be each year because it's an annual rate. So it'll just be T. So there's our equation. So let's find the population in 2025. So we want to go from 2000 to 2025. So T will be equal to 25 years. And so the population P will be equal to 6.08 multiplied by 1.0126 to the power of 25. And so when we type this in, 6.08 to the power of 1.0126 to the power of 25, And so we get the answer to be about 8.3 billion people. I think the population right now is something just over 8 billion. So this model, like I said, when they came out with this, relatively close, but again, not bad. Okay, let's continue on. Letter H. Suppose an investment of 50,000 grew to $87,040.20 in 10 years. What was the interest rate if the interest was compounded annually? Okay. So when you want to solve this kind of question, we can still use the exact same formulas before. So here we're dealing with money. So let's use M for money, I suppose. And so we're going to have M is equal to M naught times B to the power of T over D. That still doesn't change. So B, T, and D. So how much money do we end up with? 87,000. How much do we start with? Well, we start with 50,000. What's the interest rate? Well, we know for interest rate that it's going to be 1 plus some percent. So here, let's let the percent be I for interest. All right. We appear to have lost. All right. Okay, welcome back. And we'll go back. And we'll finish up this last question and then we'll call it there for the day because my computer has kicked me out, which means we must be running low on time. And so we're going to have 87,040.20 cents is equal to 50,000 times B is going to be 1 plus I to the power of T, which is going to be 10. So we divide both sides by 50,000. And so we get 87,040.20 divided by 50,000 is going to be equal to 1 plus I to the power of 10. We now need to take the 10th root of both sides. So this is something you might have done before, but this seems like a good review. And so at this point, we probably want to type this in. So we're going to have 1 plus I is equal to, and here we want to take the 10th root of $87,040.20 divided by 50,000. And we end up getting 1.057. And so minusing 1 from both sides, I is equal to 0.057, which will be an interest rate of 5.7%. And so the interest rate for this circumstance to be true, I would have to be 5.7%. And so with that, we are running low on time for today. So we will save the leftover questions for next time, for Monday. So if you have any questions, please feel free to reach out and we'll see all of you next time. Goodbye for now.